Okay, hello and welcome. It's great to see you back this afternoon. I hope you had a good break from the previous session and that you've had sufficient time to digest the information that you've received yesterday. Today we want to dive deeper into energy transparency and how to give more power to software developers. That's a mission that we are on, and I'm focusing with my research in particular on software because I think there is a lot that we can gain by making software more energy efficient. So for today, we've got questions and answers still as usual. We've also got a chat window on the right hand side for me, so I will watch this more easily today perhaps as yesterday, and we will need it a little bit because it wasn't obvious how to do polls today. Yes, so let's just dive in. Let me introduce myself again, as some of you might not have been here yesterday. I'm Kerstin Eder, Professor of Computer Science at the University of Bristol. I lead the Trustworthy Systems Laboratory and also a research group on verification and validation for safety in robots. But today we want to talk about energy transparency, and we want to carry on with where we left it yesterday. All right, so learning objectives. Let's have a look at our learning objectives, how far we got yesterday. We learned why software is key to energy efficient computing. In fact, we had a very close look at the ICT sector, its energy usage, and found out that if it was a country, it would be 6th in the world in terms of energy usage. We also found out about the carbon footprint of the ICT sector, and compared that to aviation, where we are very strongly encouraged, and many of us do, offset our carbon footprint, whilst this is, I would claim, not the case when we use ICT, because, well, we all are probably quite ignorant of how much energy is consumed by the ICT we're using. We have seen the new concept of energy transparency. We understand what that means, namely that energy consumption information is available for you, ideally without having to run a program, and also at all different levels of abstraction in the system stack. And we also understand why we need energy transparency to achieve energy efficient computing. It's really simple. If you can't see how much is used, you won't be able to optimize that. And we also have looked at how to measure the energy consumed by software. Okay, we did this in detail. We looked at a small development board or shield that sits on a host board, and from there you can start measuring the energy consumption of embedded devices. Okay, now we've also looked into how to estimate the energy consumed by software without measuring. And I just want to have a quick look at this again to get us into the right frame of mind. So static energy usage analysis, we looked at this little factorial problem yesterday. And I was saying that we extract cost relations from this program. So if I want to know how much it costs to call factorial, then that is the cost of the comparison plus the cost of the return if x is less or equal to 0. It is still the cost of the comparison if x is greater than 0, but then it is also the cost of this lower return, the last line of the code, where we also have included a recursive call. And that's basically the cost of the multiplication plus the cost of the recursive call. And so I just said yesterday that we just need to know how much these cost. That's the comparison, the first return, and then the multiplication. And if we know how much these cost, then we can just simply put these cost relations to a solver, such as pubs, and the solver will give us energy consumption functions, which are in closed form, so no recurrences in there. And this sort of static resource analysis dates back to Waitbright. There was seminal work done in 1975. I've included the reference to Communications of the ACM if you're interested in this, type of program analysis where you obtain cost functions. Okay. And then I was saying it's actually not quite as simple as this. It looks simple, but it is not as simple as this may first appear. Okay, and so it is worth us being wary that at the moment what we are seeing here is source code, and what I'm asking for in those cost relations are the costs associated with these source code operations. And really we need to find out what these costs are. This leads us to want to know how to construct energy consumption models. Okay, so in order to be able to use this type of static analysis, I need to know how much things cost. And so before we can tick off the how to estimate the energy consumed by software without measuring, we first need to learn how to construct energy consumption models. And that's what we're going to do now. So modeling is important so that we can capture the energy consumed by a computation and then use the model instead of measurement in order to figure out what the energy consumed is during the execution of a program. Okay, so let's think about modeling for energy consumption. There is the question of at what abstraction level we should model. And generally speaking, we could look at the machine code, so the instruction level. We could also consider a halfway house, that's the intermediate representation, or IR, of the compiler. Or we could wish for a source code model. Now, the source code model would probably be the most useful to the programmer, right? So as soon as I write a line of source code, I know how much energy this costs. But we know that between the source code and the actual execution on hardware, there is the compiler. So these are the three abstraction levels that we could choose, or that are obvious targets for modeling. But models also require measurements, and that means associating entities, identifiable entities, at a given level of abstraction with costs, in this case, energy consumption. Okay, and we need to think, when we do these measurements, about accuracy of the measurements. But in terms of the modeling considerations, we also need to think about the usefulness to the programmer. So in terms of accuracy, the lower the level, the higher the accuracy, because the closer to the hardware I am, and the better I can measure, the more accurately I can measure. Now, unfortunately, it's different for the usefulness, because the higher the abstraction level, the closer to the source code, the more information I can give to the programmer, so the more useful it is. Okay, some of you might argue, I don't really want to know as a programmer, there should be tools. And we've seen yesterday this ACMQ interview with Steve Ferber, where he clearly says you need to have tools. And so the intermediate representation of the compiler, so letting the compiler know, might be a good compromise between accuracy and usefulness. And we've explored exactly this. Okay. But in principle, this gives us a bit of a dilemma, right? For the accuracy, the lower the better. For usefulness of information, for being informative to the developer, well, the higher the better. And that's a bit of a dilemma. And every modeler has to think about this and make the right choice for what they want to do with their models, okay? So for us, we wanted to do static resource analysis. We've looked at what we wanted to do based on the slide that I've already shown. And we decided, instead of extracting the cost relations at the source code level, we are going to extract those cost relations at the machine code level. Right? You can do this exactly the same way. You extract the cost relations at the machine code level, and then it becomes really easy because the costs in your cost relations are then actually machine instructions. Okay, so we thought, okay, if we can associate machine instructions with costs, then it should be really easy. So we were looking for ISA level energy models. Okay, so instruction set architecture level energy models. And we found some prior work from 1996. That's a long time ago. Okay, and this work suggests that if you want to know the energy consumption of a program P, then what you need to do is you need to take into consideration the instruction base cost, BI, for every instruction in the program that is being executed as the program runs. And on the other hand, also, you need to consider how much it costs to switch the circuit between individual instructions. So the circuit state overhead for each instruction pair, IJ, needs to be considered. That accounts for anything that is not accounted for in the base cost per instruction, because when you have subsequent instructions in an instruction sequence, sometimes you need to quite significantly power parts of a circuit on and off, or change the state of the circuit in order to be able to execute the following instruction. Okay, so that is a simple energy model. Okay, so why not start simple? Here we go. Let's have a look again from a slightly different perspective. There are two components effectively to such an energy model, right? On one side, you've got the base costs and the overhead costs. These are energy costs. You can characterize them through measurements. Now you need to be very careful in constructing the instruction sequences to produce suitable execution activity in the processor so that you can measure them. Okay, so if we think about how this can possibly be done, you could construct large loops. For instance, if you want to know the base cost for a particular instruction I, you can construct large loops with individual instructions. Or if you wanted to know how much it costs to switch from one instruction to the other, then you could construct large loops of pairs of instructions to determine the switching costs. And those loops are then being measured, and then you can take an average over those observed values, and that way you can identify for each instruction and each instruction pair how much energy is consumed. Okay, and then of course we're summing this up, so we're multiplying the base cost with the number of instructions of that type, or we're multiplying the overheads with the number of instruction switches of that type, and sum that up for all pairs and for all instructions. Okay, so these ones here, these two, are energy costs that we can measure. Okay, let's have a look at the others. So we've got these two other components of an energy model. These are program specific. Right? So the NI is the number of times that instruction I is executed when the program is running, and Nij is the number of times that the execution of instruction I is followed by the execution of instruction J as the program executes. Okay, so let me go back, that was unintended. Okay, so we've got effectively two things to worry about. These two constants for each instruction and each instruction pair, which we can measure. They are not program specific. And then these counters, these numbers of occurrences, which are program specific. Okay, so let's try this out in a very simple example, and we may need some interaction with you, and we will use the chat window for that. Okay. Here we've got a very simple program, right? We've got a source code program, factorial, very simple piece of code. And the question is, how much energy does a call to this program with x being 3 cost? Okay. Now, the first thing we're going to do is we're going to translate this into machine code, right? here we've got machine code. We assume R0 contains our argument, our 3. And we've got a sequence of machine instructions that might be produced by a compiler. Okay, so here we can see subtraction, comparison, branches, different types of branches, and a multiplication as well, some labels. I assume everyone is happy with that. Okay, so now we come to the base cost characterization. In order to determine how much energy is consumed by this little program, we need to know how much it costs to run each one of those instructions. So for each instruction in the program, we need to measure the base costs, for instance, by repeatedly running large loops and observing the resource consumption, and then associating the costs that we are observing to these instructions. So we can see the subtraction, we assume, costs 600 picojoule. The multiplication is the most expensive, costs 900 picojoule, and so on. There's different branches in there as well. So these are our base costs. Okay. There are also the overheads, and that we need to characterize too. Okay, let's have a look. Here we've got all the different instructions per column and per row, and we now have the switching overhead between instruction I and instruction J. So if I want to know how much it costs to switch from a multiplication to a comparison, that's an extra 30 picojoule, right? Or if I want to switch from a subtraction to a comparison, that's an extra 20 picojoule. Okay, now in some processes this might be symmetrical, and in some processes this might not be. So here in this case we don't have it symmetrical, so that's okay. Okay, so now we've characterized our model, right? So we've got the base costs and we've got the overhead costs, the switching overhead. And with this we can now apply our model. Okay, we can take the model, we've got the base costs associated with this, and now we need to apply the model, but for that we still need those ends, right? And the question is, how do we find out those ends? How do we get to those ends? Ni is the number of times each instruction occurs, and Nij is the number of times I'm switching from instruction I to instruction J as the program is executed. How can we find this out? Any ideas in the chat window? How can we find that out? Yeah, good. Thank you. Instrumentation. So we could instrument the program, and we could then extract a trace, for instance, right? So we could instrument the program and we can extract an execution trace and then count through. Yep, that we can do. Any other ideas? Anyone else, any other ideas as to how we could go about this? We could do a static analysis of the flow graph. That's very good. Thank you very much as well. So that's another way of doing it, right? We could use static analysis, and static analysis of the control flow graph could tell us exactly that as well. So there are two options, right? There's an interesting question. Loop bounds. Loop bounds are very, very important. So in this case, we have a call to the code with an argument of 3, right? And that bounds the loops, right? So when the model is applied to a program for which we actually have the data, then the loops are naturally bound if we know what the data is, right? So we don't need to worry about this, but that's a good point. We get back to that later. Okay, so we've got various options, right? What I like is that no one actually has suggested to go into the source code and count it, right? That would not be correct, because just counting through the source code, well, the source code, let me say, the machine code, right? Just counting through the machine code doesn't tell us for a loop how often the loop will be executed, and therefore that would not be correct, right? So that would be incorrect. But here we've got a variety of different options that we could choose. Okay, that's great. So we've now figured out how we can determine these, which is great. And here is a little exercise now. I know you've all had lunch, so we need to get active a little bit. Let's assume the argument is in R0. We've got our code. Which instruction sequence is being executed for a call to factorial with argument 3? Can you try and have a go at this, please? Once you've got your instruction sequence, just put it into the chat window and we'll go from there. I assume everyone can see the chat window, so we'll use this for communication. I didn't think this was appropriate for a poll, really. I couldn't think of a way of doing this on a poll. So have a go at this and try and work out what the actual sequence of instructions is. So we don't just need to know which instructions, we also need the sequence so we can determine the overheads, right? So which instruction is followed by which other instruction. So we need the instruction sequence. Give me a sign of life if you're calculating. Aha, there we've got some. Great. So let's have a look what we have. We have got subtraction, comparison, a branch. That's right. Multiplication, subtraction, comparison, a branch. Another one, multiplication, subtraction, comparison, the branch, and then Arthur, I think you might have you might have gone around the loop once too often. Who else have we got? Subtraction, comparison, branch. Yep, so we've got some. So this is what I've come up with. Have a look and see. Does that meet your approval? Any thumbs up, thumbs down? Yeah? Okay, so now we've got the execution trace, right? We have the actual case, the execution trace. We could have obtained this through instrumentation, perhaps from a simulation, or just from executing, right? That we could also have done. Let me go one back. Okay, so now we have the execution trace and the costs. What we can now do is we can apply our energy model and calculate how much energy is consumed. So let me put it all onto one slide, right? So we've got our formula as to how we need to add things up. And we have got in this formula the base costs and the overheads. And what we can see is for the subtraction, for the comparison, for the multiplication, we've got all the base costs, we've got all the overheads, so we can calculate our energy consumed by taking 3 times the subtraction, 3 times the comparison, 1 times the bx, 2 times the multiplication, and then we've got the 2 branches, and then also we've got all the overhead costs, right? And so if we do this, we get to 6.92 nanojoule. Okay, so that would be the energy consumed by a call to factorial with the number 3 as argument. So that is the case. That's not the best case, the worst case. That is the case given the energy consumption models. Okay, now someone's already asked, is it really this simple? And the answer is it is not. Right? So I've only given you part of the story just to get you into the mood of how this works. And it's not actually that simple, because we have got other things that we need to consider. We've already seen this in the previous slide a little bit. There are other effects that we also need to account for, right? This is not as easy as it looks. There is microarchitecture typically in processors, and there are instruction effects that we need to consider that depend on the state of the circuitry. And in many cases, the microarchitectural designers are very crafty in squeezing out a little performance here and there, pipelining, caches, forwarding logic, all sorts of integrated and complex parts. And we need to account for how much it costs if they are invoked. So if the pipeline stalls, how much does that cost? If you have a cache miss, how much does that cost? If a branch is mispredicted, how much does that cost? And so these are not easily attributable to individual instructions. You can already see that this can be quite complicated as you go along, right? So it's not actually as simple as it might appear. Right, so we've been diving into instruction level energy modeling. That was our first attempt. We grabbed this model and said, okay, let's have a go at this. And in order to minimize the effects of this last box here, right, the instruction effects, the microarchitectural effects, we picked an architecture that is very simple. Okay, and that is the XMOS XS1 architecture. You can see a picture of it here. It's an embedded microprocessor. The instruction set incorporates input-output instructions, so that makes it really easy to characterize them as well. It's an event-driven architecture. It's real-time capable. It has fully deterministic execution with worst-case execution time analysis and guarantees. It's fully timing predictable. That is very good news. It's got channels for routing messages between threads, and it's based on communication between threads using message passing. It's a very neat, small little architecture. The pipeline has 4 stages. Let's have a look at the pipeline. The pipeline has 4 stages, stage 1, 2, 3, and 4, as you can see here. You can process up to 8 threads per core. The pipeline is hardware multi-threaded. That means each thread can only be once in the pipeline, right? So if we look at stage 1, we've got thread 1. Then with the next clock cycle, thread 1 moves in stage 2. Next clock cycle, thread 1 in stage 3. Next clock cycle, thread 1 in stage 4. And that gives us 4 clock cycle. That's a thread cycle, right? And then the pipeline is being filled up with other threads, and thread 1 can only appear again when it's left the pipeline in stage 4, right? So even if you've only got 2 threads in the pipeline, you would then have 2 empty slots in the pipeline, okay? So lots of complicated issues are resolved by such a simple architecture, such a simple processing method, okay? Of course, because of the simplicity, it's easy to understand it, and it's easy to analyze. And if you remember right at the beginning of yesterday, I said there are different ways of achieving trustworthiness of a system, and one is through design. And this is so simple that you can see what's going on very easily. And that also makes the analysis and the worst case execution time analysis really easy. And so we thought this would be an ideal target to start our investigation into energy consumption analysis. At 500 megahertz, you get 125 MIPS per thread, provided there are less or equal to 4 threads in the pipeline, because the pipeline is maximally loaded with 4 threads. Okay, so this is a really simple architecture. But you can see you've got concurrency, right? You have different threads in there, so they're switching between those threads, and there is concurrency involved. So how does our energy model look like? So based on the simple energy model that was inspired by Tivari's work in 1996, we developed a Tivari-style energy model for the XMOS-X core, which is a multi-threaded processor, or allows multi-threaded programs to be executed. How do we do this? Well, the first thing we need to think about is the time the processor might spend idle, right? So there is a base cost that captures how much energy is used as the processor is just switched on. And you can see that we've actually been teasing out power and time to make energy, rather than having energy costs as such. So we've got the power base, and we've got the clock period, and in the middle we've got the number of cycles where no thread is executing. Okay, so that is how much it costs to be idle. Okay, and in addition to this, we need to think about execution. Well, during the execution, we have to consider the number of concurrent threads and the cost of execution at that level of concurrency. So if we have T threads in our program, then we want to account for the thread level. We want to account for the power for each individual instruction, so that's the instruction cost. MT is the concurrency cost. And then it becomes really, really complicated with the overheads. It's almost impossible to characterize them for each pair of instruction. And we also realized they tend to be quite small. So we decided to just leave a generalized overhead that we add to all the instructions. Okay, and then there is the base cost, the base power for the processor to operate, and that needs to be considered with the number of times instruction I is executed at the concurrency level T with respect to the clock period. Okay, so that's a slightly more complex model, but actually it's inspired by what we've seen before, and still quite simple. We've used execution statistics rather than execution traces. That was significantly faster than obtaining a full execution trace. And that is possible because we decided to have the overhead to be generic. So we didn't actually need to know exactly the sequences of instructions. It's fast running with an average error margin of less than 7%. And that was suitable for our purposes. Okay. So this is the setup. How did we do this? This was prior to us having the energy shield available. So what did we do? We intercepted the power supply. That's the power supply that would normally go in the design under test. So that's the XMOS-X core. On the XMOS-X core, we have different tests that we want to run. And that's the test harness in this gray box, the test run harness. We intercepted that power supply with a shunt resistor, which you can see on the left, and we put over this a power probe to give us power samples. That's the INA 219 probe. The power samples were delivered to a master processor, which controlled the execution on the XMOS device, and the data was then transferred to a host processor for us to collect all the data. Okay, and this is more detailed description can be found in the associated paper. Okay, so what do we get? It looks really interesting. What have we got here? We've got odd threads and even threads. So thread 1, thread 2, thread 3, thread 4, so odd and even. And we have arithmetic logic instructions. They are very easy to put into tight loops. And so we focused on those ones first because they were the lowest hanging fruit. Now, the first question for us was, how can we visualize what we are seeing, and how can this make sense? Now, clearly, ordering the instructions by the instruction name alphabetically doesn't make any sense at all. So we thought about what else can we use to make any sense of this, and it became apparent that the number of operands for an instruction nicely groups these instructions, right? So what you see up to the first, if you start from the bottom left corner, you've got blue there, and you go to the first set of yellow, and you find dashes there. These are all instructions that take 2 operands, okay? So for instance, you find negation in there, or not, right? Then we have a group of instructions, which is the largest group of instructions, that take 3 operands. So the familiar ones, addition and subtraction, for instance, you have 2 operands to add together, and you put the result into another operand, right? So that's 3 registers that are being used. And then on the very edge towards the right-hand side, you've got instructions with 4, 5, and 6 operands. So 6 operand instruction typically takes 4 input operands and writes to 2 registers. Okay, so that's a long multiplication that you can see at the far right at the bottom, that L mul. Okay, right, and so what can we see? We've got power in milliwatt on the right hand side, going from blue, which is low, to red, which is high. Now, it's not surprising that the instructions that take most operands are those that consume most power, or where most power is dissipated during the operation of the instruction. That is not at all surprising. And likewise, the instructions which take fewer operands are much more energy efficient. Okay, so there's less work done, therefore the energy consumed there is lower. So we call this a heat map, and there were interesting patterns in there. And our first heat map actually looked quite different. And it was interesting for us to show that to the engineers at XMOS, some of which said, I don't understand why this instruction consumes so much energy. I really can't think of why it should. And without naming exactly which instructions they were, they went to the hardware designers and talked to them. And then they actually looked into the implementation of the instruction. And they found that although the instruction did what it was supposed to do functionally, so it did provide the correct functionality according to the instruction set manual, there were much more efficient ways of implementing that instruction. So there was an interesting discussion between the engineers as to how the functionality of particular instructions could be realized. And someone came up with a much better implementation that realized the same functionality, but it made for much more blue being present in those instructions that take 3 registers. So that was a way of debugging the RTL. Now, why didn't they spot this before? Well, they didn't spot it before because the instruction was implemented in such a way that the logic still fitted into the clock cycle. So no one really realized that there was a more efficient way of implementing the instruction. And so we started off with quite a lot of yellow here, and then it turned more blue as they found implementation bugs that could be realized in a much more efficient way. Okay. Let me go a little bit further before I look at the questions. Now this was for 32-bit data. We then run this for 8-bit data. And well, what we saw was that 8-bit data is really cool. Literally, it's cool. You can see it, right? So what's the message here? The message is next time you write int x or int I, and you know the counter will only ever go to 100, why don't you use 8-bit data instead of 32-bit data? Using smaller data widths is actually cool. And And so think about very carefully when you define your data types, and you can actually write much cooler code when you consider how the variables that you're defining are being used in your program. Okay, so that's the message I want to give. And this is not new, right? We've seen this earlier on. For those of you who have seen the lecture on machine learning accelerators given on Monday last week, you probably were more thinking about or listening and looking at these bold lines here. But if you look at it more closely, 8-bit integer add 0.03 picojoule, 32-bit integer add 0.10 picojoule, right? There is a big difference between these. So it's not just our data that shows this, but considering the bit width is really important when you code, and it can save quite a lot of energy. Okay, so just to point out that size actually does matter when it comes to data width or bit width. Right, now before I go into this, let me look at the questions. Okay, so there's an interesting question on the memory and related instructions. We're applying it only to CPU instructions. You will see a little bit more about how we've dealt with this later on as we go along, right? So this simple way of starting has a good reason, and we'll get to that later. So that will be answered live. It will be coming in later slides. The caches also we will answer later. We will see how that can work, can be accommodated in an energy model. So Willie asked a question regarding base and overhead costs, assuming no trickery of a microarchitecture and supposing a perfectly stable thermal environment, no extra leakage due to temperature. Are the static costs linear against the frequency? So if everything else is equal, I would say yes to that. But we are characterizing, so for the architectures that we are now modeling for, we are characterizing at different frequency levels. So it is okay for the model to assume that these are static I'm not entirely sure whether I understand it. Linear against the frequency. Not entirely. So if I understand it correctly, you want to basically change the frequency and then see how these costs develop. I would recommend that you actually try it out and see. I would recommend you try it out for your particular architecture and see what happens. So that's a bit of a tricky one. Okay. Right. What we haven't covered, we looked at memory. We looked at, and I said that we would deal with memory as we go along. But the X core also has communication instructions, right? And as we've only looked at arithmetic logic instructions so far, we were interested in how much it costs to communicate between different cores. And in order to do this, a communication platform was developed, which is called the Swallow platform. It's got 480 processors embedded in a stack, and they're based on the XMOS XS1 architecture. You see here the L1. The L1 is the core that we used for our first energy model. And the L2 simply contains two L1 cores, and they're connected with a fast switch so that they can communicate with each other. And then there are extra links, X links, that go to the next L2 device. Okay, and so what we asked is, let me see, we had a 7-stage filter, a biquad filter, and this filter could be implemented in various configurations on that board, on one slice of these boards. So if we go back, we're talking here in particular on one of these slices, on one of these blue slices, right? On these blue slices, you've got 16 cores per slice, and they are organized in such a way that they can communicate. Where you see the gray dots, these are the 16 cores, and these gray dots are connected with each other so that they can communicate throughout the architecture. So there's no mesh network or so. The communication links are only the ones that are visible in this picture. Okay, so we've got a 7-stage filter. That means I have 7 threads. Okay, so there's different ways of laying this out. I could, for instance, have 7 threads in one core. Remember, each core can take up to 8 threads. So I could put them all onto one core. I could decide to spread them over 7 cores, right? I just put 1 thread per core, and that gives me the orangey red distribution of work over this network. Or I could choose 2 cores, right? Remember, the best load for the XMOS core is 4 threads, because the 4 threads fit into the pipeline. The pipeline is effectively full with 4 threads. So that means I could just use 2. Okay. So what I could do is I could co-locate these. So that gives you the greeny minty color, quite close next to each other. Or I could spread them as far as possible, taking the topmost frontmost corner and the bottommost rightmost corner in the picture. Okay, so these are just some configurations that I could choose to consider. Okay, so what can we see? We've got that implemented in the different configurations. We've got consideration for power, time, and energy, which we've got graphs for at the bottom. And we've got the different configurations listed on the left-hand side of the slide. Okay, so the 7-core version is an interesting one. If I look at the 7-core version, then I basically have the pipeline least full, right? Because I'm only using 1 thread per core. And that gives me quite a high power dissipation. The execution time is the minimum that I can achieve, right? Because each thread goes through on its own. And then I've got the energy, which is the product of those, right? If I look at the bottommost line, the 1-core implementation, the 1-core is running 7 threads. That uses more time because I need to share the processing resource, because the maximum performance on the X core is with 4 threads per core. Okay, so that means it will run for longer. But in terms of energy, it actually comes out very similar to the 7-core. That's an interesting observation. And then if I've got 2 cores used, one with 3 threads, the other one with 4, and I decide to distribute them over the corner, or I co-locate them, which is the lower one of the 2-core listings, then we can see that the extra communication cost is visible by the extra power in the blue bars, right? So the top one has slightly higher power, although the execution time is the same, because the execution is the same irrespective of the physical location of the computation. And so therefore on energy, you get a higher energy consumption for the version that is distributing over the far corners of the architecture. Okay, so that allows us to see how communication affects the energy consumed. So ISO level energy modeling, to sum this up, associates costs with each machine instruction, or aims to do this. This makes the analysis at the ISA level really easy, right? Because we've seen that if I can extract cost relations at the ISA level and the energy model provides me exactly these costs, then I can just simply add things up. And that's really easy. But characterization requires crafting workloads extremely carefully, tight loops of single and pairs of instructions, and still some instructions won't be possible to characterize accurately that way. And some of you in the questions have already made that observation, right? We've only looked at the lowest hanging fruit, which were the logic and arithmetic instructions. And yeah, that's very simple for those, but there are a lot of other instructions and it's not as easy for them. And then also there's all the communication with the memory, etc. So that's not that simple. So the question is, can costs be associated with other entities, right? Are there other identifiable entities that I can associate costs with that I can then still access in a static analysis, right? Because that's the purpose of the model. Now, there are PMU-based energy models. Many architectures now offer performance monitoring units. And these performance monitoring units offer counters that allow counting of hardware events and certain statistics. So for instance, you can look at the execution time, you can look at the number of load instructions, integer instructions, floating point instructions, different instruction types. And you can look at microarchitectural features as well. So branch prediction misses, instruction or data cache misses, and so on. So with these performance counters, you can associate costs with these, right? So you can do resource consumption analysis based on those counter values. That means we need to collect data for a large number of diverse benchmarks that stress the processor and all of the different features, and use regression analysis to train an energy model. And then if I've got the counter values, the energy consumed can be estimated using the regression-based models. You can also monitor PMU counters at runtime to enable runtime power and energy monitoring. So that's also possible if you can access these PMU counters directly in the hardware. Okay. Now, that gets me to a different project. We are currently working in a project called Team Play, Time, Energy and Security Analysis for Multi and Many Core Heterogeneous Platforms. I've got the URL there. And in this project, you're now going to see the most recent work that we've done. That's an energy characterization of the ARM Cortex M0 using PMU counters. Okay, so we've looked at a large number of benchmarks, embedded benchmarks from the BEEPS benchmark suite. That's the Bristol and Embecosm embedded benchmarks. And we collected execution statistics. Now, many of you will say, hang on, the ARM Cortex M0 doesn't have PMU counters as part of the architecture. That's true. So we needed to be more inventive. There is a instruction set emulator, an open source instruction set emulator for the thumb instruction set, which is called Thumbulator. And we created a customized version of that Thumbulator. You can find the GitHub repositories for both the BEEPS and the Thumbulator version that we're using at the bottom of this slide. Okay, and so we identified some counters and used these counters for our energy modeling. Now, this might answer some of the questions that I have previously said we'll answer later. Hopefully it does. So we want to know how many instructions other than multiplication instructions have been executed in the program. RAM data reads, RAM data writes, flash data reads, and any branches that have been taken, as well as the number of multiplication instructions. Okay, so these are the counters. It's a very small set of counters that we've decided to use for our modeling. And the interesting aspect for these counters is that these counters are also statically predictable. Okay, so you can use static analysis to predict values for these counters, which is great news. Okay, so here's the model. We used linear regression. We collected a lot of data. The energy consumption estimated is given in nanojoule. And here you can now see the energy consumed by the processor given a program. We have two parts of the model, these constants. And then we've got the program-dependent parts, namely the values for these counters. Right? So given a program, I get the machine code. That machine code I get through the thumbulator. The thumbulator gives me values for all of these counters in the model. And based on those values, and given the constants, I can then calculate how much energy is consumed for the execution of this program. Okay, so this is the energy model that we are currently using. For the ARM Cortex M0. And this is not yet published work, although it is in a publicly available deliverable in the project. And in this deliverable, there is far more detail on how we set this up, how the regression worked, and why we have chosen these particular counters. One of the considerations was that we didn't want to have any extra constants in addition to the products that we have in this sum, because it would look odd if no activity was there, yet energy would be consumed. Okay, so we were very careful in terms of making sure we get a high accuracy model with counters that can be statically analyzed. Okay, let me look at our questions. That's one from Kim. Thanks, Kim. That's going back to the bicquad filter. Interesting question. What are the cores doing that are not used whilst the filters are active? The cores which are not on the same in the same package, effectively, they are doing nothing, whilst the ones that are paired, they will be idle. Okay, so that's an interesting question. Yes, that's a good question and interesting observation. One, of course, needs to think about how the hardware is used and how much is powered on, while you might only be using a very small part of what you've powered on. Thank you. Okay, so this is a more sophisticated model, right? So this captures almost everything, and we're now evaluating this. Right, that gets me to how to construct energy consumption models, right? So we've now had an investigation into the energy consumption models, and that gets us back to estimating energy consumed by software without measuring. I also realize it's an hour since we started. So what I would like to do is I would like to announce the winners of the scavenger hunt from yesterday, and then we'll have a little break. And let me switch over. So we will carry on exactly at this place later, but if I now stop sharing for a tiny moment and I show you the winners of our scavenger hunt. So let me share this. our scavenger hunt. Here it is. Okay, so yesterday I gave you a challenge. Hang on, we're not looking at the right display. Yes, that's better. So yesterday I challenged you to do a little scavenger hunt, and the submissions needed to have 8 items in them. And if you go to this link, then you should still see, I think, it's still true that you should see the submissions. So let's see what we've got. The winners are, we've selected the 4 fastest submissions. One that is most original, which we regarded to be this one where the drink is actually tied to a plant. And I did say 1 course-specific criterion. Now, using the chat window, what do you reckon that course-specific criterion could possibly have been? Ah, not the battery. Close though. Sunglasses, what I was asking. Which display are we seeing now? I was hoping we would be seeing the large screen with the pictures. Okay, let me see. I was thinking I am sharing the right screen. Is that any better? Yeah, okay, that's better. Okay, it does show me the wrong screen then at the bottom. Anyway, yeah. So these are the winners. Fastest submissions, most original, the one with the drink on the plant, and 1 course-specific criterion. The course-specific criterion was the smallest file size. Okay, so we looked at the submission with the smallest file size, because after all, this picture came along, most pictures came from quite a long way, and considering file size is really important. So there was also a prize for the picture with the smallest file size that contained all the 8 items, which is the one at the bottom with the sun hat and the sunglasses and the large clock. Okay, so congratulations to the winners. I hope you enjoyed this. I certainly have, and I have had great joy looking at all the submissions. Thanks for everyone to everyone who participated. Each of those winners will receive a HiPEAC power bank and maybe some extra goodies. To receive your prize, you need to send an email to this email address. With subject scavenger hunt, you need to attach the picture and you need to provide your home address. Okay, so congratulations to everyone who's won. And I think everyone is a winner in a sense that, you know, those who have participated have actually got out of their chairs and did something fun. And hopefully Enika can put the gallery up for everyone to see. Now for this break, I would like to encourage you to get outside. Okay, so not just to the bathroom, but go outside and submit, as you come back, a picture, a selfie, with you evidently being outside. Okay, so go outside and send us a selfie that provides us with evidence that you've been outside. There are no prizes today. The prize is to go outside and have a bit of fun. Okay, and I shall see you back in about 10 minutes, right? In about 10 minutes, so at 14:20, we'll carry on. So you can see the selfie Dropbox is already in the chat window. Okay, so 14:20 is return time and we carry on. Thank you very much. Okay, so everyone back? I hope so. Okay, it's 13:20. We shall start again. What I would like to ask is that the selfies are basically looked at, and we can hopefully at the end of the session have a good look of who's participated. Maybe HiPEAC support can have a look at that and share that as I go along, because I don't think I'll be able to do that as I'm speaking, and we won't carry on tomorrow. So it'd be nice to see who participated, and that adds a little bit of a social feel to this socially distanced time. Okay, so we have come a long way. We have looked at energy consumption models. We've considered very basic models that associate costs with instructions. We've seen that although this looks simple, is actually not, it doesn't scale to more complex architectures and microarchitectures which are sophisticated. And we've also seen that PMU-based energy models that use regression can overcome that problem. And that's really interesting insight to gain. But remember, we wanted to use these models in order to estimate the energy consumed by software without measuring, right? So that's what we wanted to do. So we need to now dive into how to do this, how to use these models exactly for this purpose. Okay, so energy consumption analysis enables energy transparency, because ultimately what we want is we want to give power to software developers, right? We want the software developers and the software development tool chain to understand how much energy is consumed by the code that is being created. Okay, similar to when you get a thermal evaluation for your house. That's what we want to do. Okay, so let's start with something really simple. There are static resource consumption analysis already around, and we're using these resource analysis at the instruction set level. Okay, so we've got XC, which is our source code for the XMOS XS1. The XC compiler creates LLVM-IR intermediate representation and then a machine executable at the ISA level. We can combine this with the ISA level energy model that we had, and we then obtain resource analysis results. So the resource analysis results is provided as an energy consumption function that is parameterized by some property of the program or its data. Okay, so as a very simple starting point. So let's have a look at this again. We've already familiarized ourselves with this. So the point where we are now at is solving the equations, because we know all the costs. We substitute these costs in. We solve all the equations using off-the-shelf solvers, and we get a result for factorial, right? So a call to factorial, given x as the parameter, is 26 times x plus 19.4 nanojoule. Okay, and that gives us this little function over here, and when we look at it, that's interesting to look at in terms of a linear function. What we see here is in light blue what the hardware measurement suggests. In green, we see the static resource analysis, which matches this rather perfectly. And then we've got an instruction simulator, which is not as accurate and is a bit off on this occasion. We use this sometimes to validate our measurements and the models, and we were very happy that the static analysis matched the hardware so closely with such a small error. That's an excellent result. And of course, we've done this for other pieces of code, Fibonacci, power of 2, and a power calculation as well. Now, I appreciate that these are not the sort of things that you would normally run in an embedded system, right? But they are starting points for us to understand how static analysis works. And that's what they were good for. Okay, so this seems to work reasonably well. You can see that the green and the blue lines are pretty much overlapping with each other. And that was an interesting and nice result when we started off with this work. Okay, so now there is a dilemma, because we have provided or done our analysis at the instruction level, but really we want to provide information that's useful for the programmer, and ideally we want to provide that information to the compiler so the compiler can do energy focused optimizations. So moving away from the underlying model risks loss of accuracy, right? So the predictions become less accurate as you move away from the model that was created at the instruction set level. But moving higher up the abstraction stack brings us closer to the original source, of the code to the developer and to the toolchain, which is where we want to exploit those models. So in an attempt to do this, we explored the options, right? So what you see here is an analysis of what is available to us. We can have, or we can see, 3 different layers, layer 1, 2, and 3. As we go up the layers, the energy modeling precision becomes less, right? So we're losing precision in the energy models. But as we go down these layers, the information that is required for the analysis is lost. In the source code, we have information that gives us insight into the data types and into the structure of the program. And during compilation, and in particular during optimization, quite a bit of that can be lost. And so if you lose that, then the analysis gets less information and can be harder to perform. Okay, so with the type of analysis that we chose, namely cost relations, the extraction of cost relations, we decided it would be worthwhile to explore the intermediate level of the compiler, so intermediate representation, and see whether we can do energy analysis at that level instead of the instruction set level. Now, the analysis itself uses horn clauses, which is a type of logic representation that can be obtained from any one of these abstraction levels of the code. So you can translate the ISA into horn clauses, you can translate the LLVM-IR, whether it's optimized or not, into horn clauses, and you can even translate the source code into horn clauses. Okay, and then the analysis doesn't really care about what the horn clauses represents. It's always the same generic analysis that gives us an energy consumption estimation or function. Okay. So, bearing this in mind, what we needed to do is we needed to lift the energy model that we've got on the ISA level to the LLVM-IR level. Okay, and for that you can use a trick. As the source code is compiled down to the machine code, there is debug information so that you can track source code lines all the way down to the executable. Okay, that's normally used for debugging, and we've actually used that in order to link the generated machine code to where it was generated from in terms of the intermediate representation of the compiler. So if we read this multicolored graph from right to left, then on the right hand side I've got the machine code, and for each machine instruction I've got a cost, right? And as this machine code was created, on the right hand side you see numbers 13, 72, 74, 75, and so on. This is where these machine instructions came from with respect to the intermediate representation in the compiler. So now, if we associate the cost of the machine instructions and sum these up and attribute them to the LLVM-IR, then we can determine for each LLVM-IR block how much it costs when it's executed. Okay, so this is a little trick that we can play to effectively map and lift the ISA level energy model into the compiler. Okay, now let's have a look at that mapping, which is more described in more detail in the publications listed here. But if we look at that mapping in more detail, what do we get? We've got the source code. We've got LLVM as a compiler. We get the LLVM optimized in intermediate representation. We've got the ISA level energy model in the middle here. And we are then performing that trick to remember where the machine code came from, right? So we're remembering where in the intermediate representation the machine code originated from, right? So we use the debug information to keep track of this. And as we are lowering the code down, the ISA retains that debug information that allows us then to do a mapping between the cost of the ISA instructions up to the LLVM IR. And that gives us LLVM IR characterized energy characterization. Okay, and that energy characterized LLVM IR still then needs to be tuned, etc. So there's a tuning phase at the end of this process, and then we get energy characterized basic blocks. That's really good, because that means the compiler can see those, and the compiler can compare different options of code and look into what is the most energy efficient way of realizing a piece of source code. So that's really an interesting achievement. Okay. So with this trick in mind, we can now lift our resource analysis, because remember I said the resource analysis works on horn clauses and it doesn't really care what the horn clauses represent. So we started off applying our resource analysis on the left-hand side here to the ISA level. But now with this trick that we have lifted the energy model from the ISA level to the LLVM IR level using a mapping, we can apply our resource analysis to the LLVM IR level and see how we are doing at that level. And it's exactly the same resource analysis tool. Okay. So how are we doing? We've got our results from this endeavor. We see here different types of programs. The first group of these programs, they could be analyzed both at LLVM and ISA level. Okay, and you can see here in the table the error versus the hardware measurement, right? And you can see that at the LLVM level, the results are acceptable, right? So, and that's a really good result. For the second group of programs, you see that it was not possible to analyze these programs at the ISA level, and that is because critical information about these programs got lost during the translation down into machine instructions, and the extraction of recurrence equations, etc., was hampered that way. But much of that information can be retained at the LLVM level. Okay, and so that made these programs analyzable, and you can see that the results at the LLVM level are actually quite good when compared to hardware measurements. So that's a really good insight, and we were very surprised that the mapping and the analysis worked so well when lifted up higher in the system stack. Okay, so what are the limitations of our static resource analysis? The one that uses cost relations, right? We've seen that the analysis at the ISA level is reasonably accurate, 3.9% average error when compared to hardware measurements. But a lot of information is lost during compilation, program structure, data type information, etc., which makes this very difficult, and that limits the cost relation-based analysis at the ISA level. Because the LLVM IR preserves much of this information, a much larger set of programs becomes analyzable, and the accuracy at the LLVM IR level is still acceptable with a very low average error versus hardware measurements. So the analysis at the LLVM IR level is more powerful than that at the ISA level with acceptable levels of accuracy. Now, ultimately, cost relation-based analysis is only as powerful as the solvers available for the cost relations. And that's the ultimate limiting factor that we found. And so we asked the question, is there a different way? Is there an alternative that one can use? Okay, let me see. Before we dive into this, I would like to see, there were some questions, what they have been. Okay, in terms of the debug information, Pietro, interesting question. It is tricky. It is tricky. we are basically hijacking the normal debug information at the LLVMIR level and enabling that mapping. And that is the optimized version already. So we have gone through optimization before we do that. Otherwise, we'd lose all that information. If you want to know more detail, look into the paper. It is a tricky process, but it can be done. Regarding the debug info. Yes, so the Baram also asked about optimizations. In terms of the optimizations, this is being performed on the optimized code, okay? Otherwise, that would be rather tricky. Okay. Right, so we have looked at static resource analysis using recurrence equations and found it was limited. Okay, so we asked, is there a different way of doing it? Implicit path enumeration is another static resource analysis technique. And those who've attended Tullio's session earlier on will have seen this. Static resource analysis can be done using what is called HiPEAC, and that is typically used for worst case execution time analysis. I've asked Tullio and he said I can reuse his slides. So just as a reminder, if we were to compute worst case execution time, which is where this technique was pioneered, the worst case execution time bounds have to be safe and tight. Safe so that there is no underestimation. And so if you look at the orange or red bit in the graph, you want to make sure that where you put your bound, it is not possible to then have an actual value that is higher, right? So it has to be safe. But it also needs to be tight. So saying infinitely long isn't good enough, okay? So it has to be tight. You want to minimize the overestimation for these worst case execution time bounds to be useful, okay? So to analyze a program without executing it, you need an abstract model of the target hardware. Whoops. You need an abstract model of the target hardware, as well as the binary executable, and then you proceed with high-level and low-level analysis. You then go through the compiler, you've got your source code, you've got your input data, you build the control flow graph, you do the flow analysis, you do the low-level analysis, you formulate an ILP problem, and then you solve it, you get the worst-case execution time. Okay, all done and dusted. Implicit path enumeration again, shown here with the flow graph analysis and the maximization. Okay, so that's an interesting option, we thought. So all we need to do is investigate this as a way of doing energy consumption analysis. Okay, so we're going to use implicit path enumeration. We use a model of the hardware, and the resource consumption depends on the control flow of the program and the behavior of the hardware, right? So we can use it as for energy analysis. And there were a lot of people who contacted us to want to do this as well. So that seems to be the way forward, right? So energy analysis with HiPEAC. Okay, we've got the source code, we've got user annotations. The user annotations can, for instance, tell us something about the loop bounds. We put this into the compiler, we get the control flow analysis, we got the low-level analysis. Based on this, we do the computation, the implicit path enumeration technique, and then we get energy estimations. Sounds good? Let's go for it. Okay, so here is our energy analysis. You can see a large number of benchmarks, smaller ones and larger ones. The line 0 is hardware, is where the hardware measured result is. And we have a simulator that is used as a sanity checker. And then we've got the ISA-based static resource analysis, which is HiPEAC-based. And we've got the LLVM-based static resource analysis, which is also HiPEAC-based. And it's actually quite nice to see that all the results are, except for one there, are within plus minus 10%. The yellow one is the simulation, but all the static analysis results are within a 10% boundary. That looks satisfactory. And we've got quite a close match between the green and the purple bars. So there isn't much accuracy lost in terms of the LLVM IR-based analysis. Right? So that's good. We can make this data available to the compiler, and the compiler can perhaps then compare different versions. Okay, so different code versions to see which ones are the most energy efficient. So we were quite happy with this. We also worked out that this analysis can be used for something slightly different, namely to identify possible security vulnerabilities, right? So in some embedded systems, division might not be supported by the hardware. Instead, you have that as part of the software that's running on the platform. And on the left-hand side here, we have a collection of sample runs with dividend and divisor, and we have collected the energy in joules, and the blue dots are the hardware measurements. Then we've got worst case energy consumption in green at the ISA level, and worst case energy consumption in red at the LLVM IR level. Both of them nicely coincide at the top for this particular radix 4 division code, and they give us the upper bound. And we actually, in this case, were able to brute force the worst case because we knew what the data was that would get there. And so that's interesting. But what we see here is that for some data points, they at the bottom, where you've got the best case energy consumption, the lowest, we actually have some data which is falling and dropping out and sticking out like a sore thumb. They have something in common, these data points. And what we found is that there was actually a shortcut in this code that, given certain values of data, would exit the code early. And that could potentially be a security vulnerability in embedded code. And so we removed that early exit, right? So that early exit was removed, and that got us to the rightmost graph on the right-hand side. And there you can see that the average has increased in terms of energy consumption. However, those parts that were previously sticking out because the data was taking the early exit are no longer that identifiable and compared to the other data points, right? So that was an interesting observation for us, that you can actually use this sort of analysis to help us identify areas where vulnerabilities could potentially be detected based on an energy model. Okay, now I also said that profiling-based estimation can be used, and so based on what we've seen so far, that's really, really easy. For profiling, what we do is we use the source code, we push that through the compiler, and the optimizer, we get our optimized LLVM IR, and then we go through different paths, 2 different paths. The energy consumption estimation and the profiling, right? The profiling is basically going through an instrumentation pass where I've got the LLVM IR with basic the basic blocks instrumented. I push this through the backend, and then I can see the basic block's execution counts. So I basically want to know how often each basic block is executed whilst the program is running, right? And with that information, and given the energy consumed by each basic block, which we've already obtained from the energy characterization that I previously introduced for the static analysis, I can then, based on the basic block count and the basic block energy characterization, determine the program's energy consumption. Okay, and so that's really easy and an easy step in case it is not possible to do the static analysis, right? So that's another option. And for this option, we've also looked at the profiling results in comparison to simulation. And again, the results are pretty useful and all within the 10%, except for one. Okay, so that's pretty reliable. Okay, so we've now looked at two different types of static resource analysis, based on cost relations and based on HiPEAC. Okay, and so I think I can tick this off. No one's asked a question yet on this, so let's have a look. Now and next, we need to learn why timing and energy analysis differ. Okay, so here's the bad news. So what's the worst case? The worst case is if you get repeatedly a research paper rejected. Would anyone agree with that? Anyone in the chat? Okay, so all the stuff that I've shown you so far, we tried to get published and we got it back several times as rejected. Why? The reviewer said that they didn't like the way we presented the results because we couldn't guarantee worst case. Let's have a look what happened. So I said we characterize originally at the ISA level, okay, and we've looked at this heat map before. And indeed, this heat map attributes a single cost to each instruction, right? So if we look at this, there is only a single cost for each one of the instructions. So we could pick one out here, maybe the add instruction, which is roughly in the middle at the bottom. You go up there and you see in the diagonal here, that is when you run add in a tight loop with only add instructions. And when you do this, you get a particular value there, and then you get the overheads when you run the add in combination with other instructions. Okay, so, but the fact is, we've got a single cost attributed. How did we get to that single cost? We used valid data for each instruction, and we chose that data randomly, right? And so the outcome of this process is then therefore an average value observed over the measurements, right? So we had a type loop of add instructions, randomly chose data, and that is valid for add instructions, and then observed the power consumed and averaged that out and attributed that cost to the add instruction, as you would. Okay. Now, remember static resource bound analysis, right? It's a bound analysis. There is a fundamental mismatch between the model versus the analysis, because we are after a worst case bound, right? So let's recap this. Worst case execution time analysis, we looked at this before, requires a worst case execution time model, right? And that means that for every instruction, you need to know what the longest time is that it needs to be, it is required for its execution, okay? So, and that's measured in clock cycles, right? And you need that model. And then you can determine worst case execution time bounds, which are safe and tight, okay? Does this work for energy consumption, is the question. Can we just transfer this? And can we just use, instead of the worst case execution time model, can we use an energy model? Okay. Now, worst case energy consumption analysis goes well beyond worst case execution time analysis. And I'd like to dwell on this for a little while to see what you think. So fire your questions away. It's a really interesting area. Okay. Now let's have a look. Embedded real-time systems that are timing predictable execute instructions in a fixed number of clock cycles. Okay. And that's the number of clock cycles that is used by worst case execution time analysis. Okay. So executing a single instruction is effectively largely independent from the data the instruction takes, right? The clock cycle is effectively the constraint that must be met for the signals to reach the state holding logic, if you think about how synchronous logic works. So any timing variability that is attributable to data for the execution of a single instruction has mostly been eliminated by design because we use synchronous logic, right? And worst case execution time then depends only on the worst case execution path in your code. Any comments? Any questions on this? In other words, if I took away the clock cycle from the worst case execution time community, that would give them a really hard time. Energy consumption, however, is data dependent. Okay, so let's have a look. Energy consumption, I'm claiming, is data dependent, and there's a fundamental mismatch here to how time is handled, because we benefit from the synchronous logic. Okay, so let's have a look at this again. We've seen this before, and let's focus in on a particular instruction. And a very interesting one is the subtraction here. Okay, so subtraction is nicely green there, somewhere in the middle, and has got a single value attached to it. Okay, but if we zoom into this and do this exhaustively for all 8-bit values, we get this picture. That isn't green, is it? That's half blue and half red. And if you average this, it gets you green. But none of this is green at all. So what's happening here? Let's have a look. So if you come with me, on the left-hand side, on the y-axis, we've got operand 1, and on the x-axis, we've got operand 2. So if we focus on the 160 here, and we subtract operand 2, as long as we are subtracting, and you go to the right and follow that line, as long as we are subtracting values that are smaller than 160, we are in the blue range. In the blue range, in the blue range, in the blue range, until we hit the diagonal. That is where we're taking 160 from 160. And then once we're on the diagonal, we're actually getting red values. Red energy consumption, it switches over. Why is that? Anyone, any idea as to why that might be? What's happening here? Any ideas? Carries? Yeah, high bits are inverted, yes. Switching activities, very good, very good. You're on the right track. It's the switching activity. Why is it the switching activity? The high bits are inverted. That's 2's complement for us, right? So that is the effect of 2's complement. 2's complement is expensive. It causes a lot of switching in the circuitry when you're going, when you're frequently changing between positive and negative numbers. Okay, that is what 2's complement does for us. And it would be pretty useful if I did energy analysis to know whether I'm in the blue part or whether I'm computing in the red part, right? And so you can see here that energy consumption is actually data dependent. This instruction uses exactly the same amount of time for all the different data values that we've pushed through, but the energy consumed is different for the different data values, right? And so we don't have the equivalent of a clock cycle, right? This computation fits exactly into the same amount of time, yet is very different in terms of the energy consumed. And that's really, really interesting. So this inspired us to look a little deeper, right? So we looked a little deeper, that's our subtract. We've looked at an add. We also looked at a shift left. And we looked, and that's possibly the most beautiful, at a logic and. Okay, and now we got the full picture, right? Now we got the full picture. energy consumption, let me go back, is actually data dependent, right? All these operations use exactly the same time for the given data, but the energy consumed is vastly different, right? You go from blue to red and back again. And so it's not obvious to determine what one should use as the worst case and the best case, and what's the average case? What does that mean? So effectively, for each one of these graphs, heat maps, the worst case is wherever it is reddest, and the best case is wherever it is bluest. Okay, this is a really interesting observation to make. Notice that the scales are different for each of the different graphs, right? So we've been digging deep into this to make sure that any observable difference are actually observable. Okay. Now we all know that A times B is the same as B times A. Okay. But the question really is the energy consumed when you do A times B the same as the energy consumed when you do B times A, right? And what we see here is a multiplication instruction exhaustively tested out for all 8-bit values on an AVR. And that these graphs, they take about 3 to 4 weeks to measure out. Because you don't just want to take one measurement, you do this repeatedly to gain confidence that you got it right. But if it was the case that the energy consumed by these two multiplications are actually the same, then this graph would be symmetrical on this diagonal. And you can clearly see that it is not, right? So that allows us to conclude that the energy consumed by A times B is not equal in all cases to the energy consumed by B times A. It's also an interesting optimization potential because by swapping the operands around, you can possibly save some energy. And I think as school kids, we all figured that out, right? With long multiplication, some of us just turned it around, get the same result, and find one of the operations easier than the other. So that's not surprising that this is also the case for hardware. Okay, so there is concern here that we cannot just easily transfer the techniques used for worst case execution time analysis to worst case energy consumption. Okay, let me see whether there are any questions. Yes, that's right. Sign magnitude representation is an interesting alternative to two's complement, and it would be interesting to look into a project where you use sign magnitude versus two's complement, and it'll probably be quite application specific. But I think what we can learn from the subtraction and the effect of the two's complement, as we've seen, is that if it is possible for us to add an offset to our calculation and push it into the positive side, do the calculation there, and then take the offset off, then that might be more energy efficient than doing the calculation with the original numbers, which might oscillate between positive and negative. Okay, so that might be something that we can learn from this insight. Okay, but it would be interesting to see whether other number encodings offer more energy efficient solutions. But then that comes at the cost of more hardware, right? Because there are very big benefits to two's complement and the way hardware exploits that. Okay. There is a question of why is the energy of A times B not the same as B times A? Interesting question, but I suggest you try out a long multiplication where one of the operands is maybe a 2-digit number and the other one is a lot larger, and see how the calculation goes and how many steps and how many multiplications and additions, and then you can add this together and see. But if you looked into a multiplier, then you will see that it also doesn't treat both arguments to the multiplications the same. And because it doesn't treat both of them the same, there is different energy consumption depending on how the calculation uses the logic. Okay, so I hope that answers your question. Have a go and see, do a long multiplication and observe and smile. Joseph has an interesting question. Couldn't the worst case energy just be determined by taking from the most read regions for each instruction? That's a good idea. So if we just go back to here, let me go back and say, okay, for my worst case energy model, I'm going to pick the reddest point in each one of the instructions, and I'm going to make that the worst case. So I attribute that to that instruction, the cost of the energy cost that is attributed to the hottest point, effectively. Now that's that will certainly give you a worst case, but remember, the idea is that it's both safe and tight, and the criterion tightness might not be satisfiable, because if you take that approach, then you will find that it's horribly overestimating. Why is this, you might ask? That is because it is unlikely that the data that caused the worst case for one instruction produces a result that also triggers the worst case for the next instruction, and the next instruction, and the next instruction. Okay, and we've got some interesting data on this, and I'll show you a little bit later. But this consideration that actually is not just individual instructions, but it's instruction sequences, and the criterion of tightness basically would go out of the window if I took for every instruction just the hottest, the reddest point. Right? So that might seem like a way out, but it's not actually such a useful way out, because horrible overestimation isn't going to be helping us a lot. Okay. Okay, so we've learned an awful lot so far, and we've gone through this. What can I summarize? Data-dependent switching costs can be large, about 30%. Okay, some instructions can cause as much dynamic energy as static energy, such as the subtraction. If you switch regularly from the blue to the red triangle. And so therefore, how can we account for context-dependent switching costs? Can worst case energy consumption be safe as well as tight, is really the question we need to focus on. Okay, so we looked at statistical ways of energy modeling, right? So many instructions exhibit statistical properties in terms of the energy distributions they have. And it might be possible to compose them. And if we then look at the worst case, namely the statistically impassable energy, we could perhaps consider this as a safe upper bound. Okay, and if you would like to read more about this, I recommend you have a look into this paper, where we went to town on this and investigated what it means to strive for the worst case, and to find the data that causes the worst case, and to try and fit different distributions and make any sense of the data that we got. Okay, so what have we learned so far? Energy is data dependent. Okay, even for individual instructions, we can observe significant differences that we cannot simply ignore. Picking the worst point for each instruction gives us over approximation, so we're ending up with bounds that are not tight. So really what we want to do is we want data-dependent energy models. And there are some few critical questions for worst-case energy consumption modeling that we need to answer. Namely, which data should be used to characterize worst-case energy consumption models? So what should you use for characterization, for measuring? Right? Because when you measure, you need to have data. Which data causes the worst case energy consumption for a given program, right? So when you've got machine instruction, the whole program, you've got sequences of instructions. We want to know what is the data that causes the worst case for this given program, which means we should ask which data triggers the most switching during the execution of the program, right? So that is really the question. And that's a really tricky question. So let's have a look at an instruction sequence. We wanted to know, does the data that causes high energy consumption in the first instruction of an instruction stream also do so in the second, third, fourth, and so on? So is that a good approximation? And so we chose 100 random data values and provided those to a sequence of 8 instructions. And then we ranked these instructions according to the energy that was consumed up to instruction X, so from 1 to 8. Okay, so if we do this for the input, then we can this graph. So after the first instruction, if I order my instructions from 0 to 100, with 100 meaning it's the highest in energy consumed after one instruction is being executed with the given data, to the lowest at the 0, right? So that's the data that caused the lowest energy consumption, right? And so if I look at this and then look at the end result after 8 instructions, what I can see is that some of the data that initially caused quite high energy consumption actually ends up quite low at the end, right? And likewise, if I have data that initially causes low energy consumption, some of it goes quite high. Right? So that's clearly showing that knowing what you have after one instruction means nothing in terms of the next instructions. And it actually looks quite chaotic. We thought, okay, do it the other way around and do it by output. Let's look at the output, the lowest energy output, and trace that back to the input. What was the input for that? And again, you can see that this is actually quite tricky. It is not possible to say that if you've got low energy at the end, in the last, by the end of the instruction sequence, that was already predictable to start with. Okay, so this motivated us to write a paper on the limitations of analyzing worst-case dynamic energy of processing. This paper makes some very interesting observations, namely that determining switching costs is NP hard. The amount of computation required increases exponentially with the program size, and it is not possible to approximate the problem accurately. So there is no algorithm that efficiently can find the worst-case dynamic energy for a given program or instruction sequence. So therefore we need to ask other questions. Is a less general solution acceptable? What's the level of inaccuracy that we can tolerate? Can we sacrifice safety for tightness? I mean, the solution for safety is clear, right? We take the reddest point for each instruction, but that doesn't give us something tight. Maybe that's what we want. Alternatively, we might have to live with losing safety for the benefit of tightness. And that seems to be the preferred option. So talking to people in industry, they seem to say, well, it would be nice to have that reasonably accurate, even if it underestimates occasionally. So it's not safe. It can't be relied upon. But that seems to be an interesting observation that one can make. Okay, Kim has made an interesting, posted an interesting question. Yes, indeed. The problem here is very similar to some of the problems that are faced by designing for test, built-in self-test, it's actually possible to show an analogy with this problem, with this switching problem, because ultimately this is a problem of how much switching is going on in the circuitry. And it's possible to show that there are analogies between this problem and a lot of design for test problems as well, for which good heuristics exist, but the computational hardness of this is clearly a theoretical limitation. And unfortunately, there are quite a few papers out there who claim that the authors have found a worst-case energy consumption model, and then they're performing worst-case energy consumption analysis. And because of the existence of these papers, our papers were rejected, because what we said is it is not possible to do this. And so instead, our energy consumption analysis is not safe. And so we cannot guarantee that the analysis provides us with a worst case. So that's a bit of theory. If you are interested in our reasoning, please have a look at the paper. It's available from the ACM website, but also all our papers are available in preprint version on arXiv, all for free. Okay, so worst case energy consumption needs to be taken with a pinch of salt. It is not a stupid question to ask what model was used, whether the analysis results are both safe and tight. And if that is the case, ask how they did it and let me know. I'd quite like to know about it. Okay, so in this paper we made another interesting observation, which I'd like to share with you. Okay, so this is a add instruction, and we've seen this picture before. We see the dynamic power of the add instruction in milliwatt for exhaustively using 8-bit operands as operand 1 and 2. Now, if we look at the data path, the cost that is not associated with the computation, but actually the data path switching, then we can make an interesting observation. So clearly this picture looks very similar in terms of the pattern. It just looks like a black and white version of the picture at the top. Now the bottom picture shows the Hamming weight of the output data path in the number of bits set. Right? So on the right hand side you've got a scale that goes from 0-bit set to 8-bit set in the result, in the output data path of this addition. Okay, so that's interesting. So we can see that where it's darkest in the black and white picture, that's where 8 bits are set. That also coincides nicely where it's reddest in the picture above, which consumes most energy. Well, that's no longer surprising, right? We know that the bit flips and transporting bits is expensive, so that doesn't surprise us. Now, if I do one step, if I take the dynamic power in milliwatt for the add instruction as in the multicolored picture on the left, and I take off the output data path cost by subtracting the energy cost associated with the bits, assuming 4.4 milliwatt per bit, then I get an interesting pattern. That pattern is an underlying pattern of the original on the left-hand side, right? You can see these quadrants. And so that's interesting in itself. Now, if I do the same for the input operands, so I take the Hamming weight of both input operands to the add instruction and the number of bits set. So 2 times 8 bits gives us 16. Okay, then I get exactly that. And it looks like a black and white version of what we see above, right? And now, and that's on the input data path. Now, if I assume a cost of 1.3 milliwatt per bit, and I take that, I subtract that from the original dynamic power, then I get this picture, which also shows us what is left for the data, for the output data path, right? And so then if I take both of them off the original, then that's left for the computation, which is really, really interesting as a base cost. Okay, so that shows us that data path switching is actually extremely costly, and it dominates what's going on in the energy consumption. Okay, so now let me sum this up. To achieve energy transparency, we need energy models. Now, energy modeling is a challenge in its own right. There are fundamental research questions in terms of worst case energy models, data-dependent energy models, compositional. Can they be made compositional? Can we use probabilistic techniques? Can we do any better than what we have currently done to allow us to do estimations of energy consumption that are both safe and also tight, and we can say that with confidence. So there's a lot of fundamental research that still needs to be done, and maybe some of you are interested in this. In terms of analysis techniques for energy consumption, static resource analysis works very well for IoT type small embedded systems. And we've seen two types of static resource analysis, the type that is using recurrence equations and the other type that uses HiPEAC. Now with the recurrence equations, you can get energy consumption functions. With HiPEAC, you typically expect a single value, but then you can plot these values as well, and you can do the analysis and get a graph that way. Hybrid and profiling-based techniques are for more complex architectures for which you can get regression-based energy models and then use them with profiling. And hopefully you have also got a small insight into that aspect. Now, as disappointing as it was to have our papers rejected and eventually accepted, together with the paper that showed that it's theoretically impossible to do, which has got an interesting message for everyone who is starting off in their research career, right? If you think you're right, push further, right? Don't go with the flow. We were very tempted to say, let's step a step back and do what others do and just not talk about the data we've used and just claim it's an energy model that is worst case. But that would be to do what is easy, not what is right. And so I hope that everyone who's listened to this has become more curious and hopefully becomes much more inquisitive when they meet someone next who claims they've done worst case energy consumption analysis. Okay, right. But as disappointing as it was to have our papers rejected, we actually won a competition. We won a competition that on the beauty of data. I submitted for the team, and we won a competition because people thought aesthetically pleasing, this is effectively art. And if anything came out of this, you can have your paper rejected, but you can still win an art competition. Okay, I was only the runner-up, the second prize, but hey, that cheered us up immensely at a time when it was very difficult to publish our papers. Okay, so now, I hope that I have primed you towards being very careful about energy analysis and that you can, with confidence, explain to someone why timing and energy differ, especially when it comes to worst case analysis. Okay, so you're now armed. You're some of the very few people who know the difference and who hopefully can explain that well. So, why energy consumption should be promoted to a first-class software design objective is our last point. Right, and that gets me towards energy-aware software engineering. Now, if we look at hardware design, hardware designers have had power as a first and last order design constraint for more than a decade. And I've looked at some interesting slides that have been presented at an energy symposium in Berkeley, where the presenter said every design is a point in a 2D plane, right? And that was in a presentation on scaling power to the future of CMOS. So he showed this. He said every design is a point in a 2D plane, and you can then optimize energy, right? Energy versus performance, and you can even see that there might be a frontier along which you find the most optimal solutions. The problem is this is available to hardware developers, but as a software developer, You don't have that at the moment. There is nothing there that you can look at with confidence and know that you've picked the right algorithm. It does fit well with the hardware. You haven't overlooked an option, and in particular, there are no tools available that help you do this. Okay, so what I'm saying is we need to give more power to software developers. What we want to do is we want to have full energy transparency from hardware to software. Really what I want to write is something like in 5 picojoule do, and then some code. And the compiler compiles this for me, and it comes back with executable code that satisfies my requirement. Or the compiler gives me a constraint that says, well, as long as your data or your program or your environment conditions are like this, then you will be able to fulfill this constraint, but otherwise it's not possible to fulfill it. Okay. The compiler might use this to search for different options, placing code in different parts of memory, or choosing different encodings or optimization levels to pick the right code that satisfies my constraints. Okay, so I want new programming models that allow me to include exactly this as part of my code. What I would like to see is that you in particular, and also the students that we are having in the next generation, actually create cool code for green software. It would be really nice to have a cool programming competition, because I think if people were to become more aware of the energy consumed by the code they write, and they could look at someone else's and see how they did it, then we would gain a lot more understanding as to what is green and what is not. So energy rated software, for instance, might be a way forward. So that gives me the right to say that promoting energy efficiency to a first-class software design goal will at least put us at par with the hardware designers, right? So that will give us the same tools and the same sort of power that hardware designers have when they come to their decisions. And as software developers, we deserve equally well. And a lot of research should be invested into making software a lot greener. Right, so that means we've also covered our last objective. We've gone through all of these objectives, and that leaves me to look at some questions that might have come in. Let me look. Any further questions in terms of the energy stuff? No, any other questions? If there are no other questions, then I would like to thank you for participating, for engaging with questions, with the chat, with listening carefully and patiently. You've been a wonderful audience. It's been fun to look at your questions and to interact with you. Thanks to all these who have participated in the scavenger hunt. For me, that was great to see, and I hope you can also see the gallery. And I'd like to also thank all my team. So most of the people who you see on this picture have contributed to the publications that you've seen, and worked really hard on getting the heat maps together. 3 to 4 weeks worth of measurement for all the heat maps. It's a lot of work, and most of these actually were sticking with it in terms of taking the rejections and trying to explain to the community what actually happens when it comes to energy versus time and how they differ. Okay, so thank you very much. At this stage, I think I'm done with my presentation. What I was hoping for is that I can hand back to HiPEAC to perhaps show us the gallery of selfies that has been created over the middle break. Shall we try and do this and see how this goes? Thanks very much for being my audience for the last 2 days. I must say I found this really hard because not directly interacting and seeing anyone is really difficult, but I hope you've learned something new, something that inspires you and that is effectively new. Right, so I shall stop sharing my screen and we go back to HiPEAC. Thank you very much. It's a pleasure to be here. That's great. Absolute great. Thank you very much for participating. It's such a shame that we don't have the social aspect, but we have got ways of dealing with this, right? We have ways of overcoming this and participating regardless. So those of you who have been selected as winners from the scavenger hunt yesterday, we'll put the slides up so you can see what you need to do in case you haven't taken a screenshot at the time the slides were up with the instructions as to what you need to do. Okay, thanks very much. I hope you enjoyed this and good luck with the rest of the summer school, and hopefully we'll see you at some stage in the future where we will hold another summer school with HiPEAC. Thank you.